there are two more topics we have to cover before we can close vector calculus. I want to refresh your memory about scalar Laplacian and vector Laplacian, but I want to most emphasize on two null identities. So first one, scalar Laplacian, by definition, it works on a scalar field, but the writing system implies you are making a twice differentiation. So whenever you see this delta function, capitalized delta, it means differentiation, and you have it squared. So you're trying to perform a twice differentiation on a scalar field. So the scalar field is defined as V, and the first operation, the first differentiation you're operating on a scalar function should be therefore gradient. So once you perform the gradient, in Cartesian coordinate, gradient is giving you a vector. So the x component is your scalar field making a partial derivative in the x direction, and then the y component is del v del y, z component del v del z. So essentially you have a vector. Scalar Laplacian implies you start from a scalar, you perform a twice differentiation, but you arrive at still a scalar. So now you have a vector and you want to perform differentiation and you arrive at a scalar, so the only choice you have is divergence. Okay? Because essentially in Cartesian coordinate, we know that divergence is trying to apply differentiation for all the components and you add them up, so you arrive at a scalar function. So the scalar initially becomes a vector after performing gradient operation, and then the vector is applied with divergence operation, you arrive at scalar. Okay? So in Cartesian coordinate, scalar Laplacian is nothing than your scalar function making a double differentiation in both x, y, and z directions. So now we can move on to vector Laplacian. The definition is quite complicated, right? So this is for you to memorize. But in Cartesian coordinate, it's easy. It's just each component, after you perform vector Laplacian, you operate on the vector and you arrive at a vector. So the x component is just the x component of your initial vector performing a scalar Laplacian. Okay, so you add this all up. So how many terms do you have in total? This is the scalar Laplacian. It contains 3 terms, 3 double differentiation terms. Right? For each one of them, you have 3 terms. So you total have 9 terms. So it can be complicated. But this is an operation that we will use in the later part of this class. Okay, just remember it. For now, you probably don't really need it, but yeah, in the last chapter for this class, we are going to use it heavily. So I will try to refresh your memory by that point. What I want to emphasize for this class is the 2 null identities. Null means 0. So there are certain type of vector operations that would guarantee you have a 0 result. So the first one is, if you have a scalar field, you perform its gradient, and then you perform its curl operation. it is guaranteed to be 0. I'm sure you learned this already, and for many times, but you don't really know how to understand it, and therefore you cannot remember it. So I think my job function is to help you to understand it in a physical sense. We just talked about curl operation, right? Gradient over a scalar function gives you a vector. So the curl operates on the vector, but why is it always 0? How can you understand it? So my job function, let me try to help you to understand. For example, I'm trying my very best. If you understand what I'm drawing, do you know what I'm drawing? Type A 101. Type A 101, you have a lot of floors, right? Different floors. 101 floors. So each floor is having different height or different potential. So I call this height as my scalar function v. V equals the height. So if you perform gradient of v for type A 101, which direction would it point to? The change in height, right? Gradient means the maximum amount of change and in which direction. So if you type gradient of v for type A 101, right? Points upwards. You ascend, you gain in height, and in that direction, in the shortest direction. Normal to the floors. So now you have to think. Now you want to perform the curl operation on the gradient. This is a unidirectional field, right? It's unidirectional. So if you walk in a closed loop, there's nothing to give you net circulation. If you walk on the same floor, gradient of v is perpendicular to your closed path. You don't gain anything, right? You're walking on the same height, you don't gain any potential. And because this grad v is unidirectional, even though you walk in a closed path, this work will be cancelled by this work. So they cancel out. So essentially, I'm trying to help you to understand the meaning of this one. If you have a field, a vector field, which can be written as gradient of v, this field is most likely unidirectional. It is a conserved field. For conserved field, you do not have net circulation. And net circulation means curl operation. Okay? So try to understand it, try to embrace it by physical meaning rather than just by mathematical formula. If you have a conserved field, radiating or unidirectional field, like the grad v I'm showing you, it cannot give you net circulation. Just think of the height, think of gravity. They don't give you non-zero result when you start from one point and you come back to the same point. So the physical meaning is a conservative field. When your field, vector field, you take its curl is 0, that vector field is conserved field, like the height, like the electric field actually, okay? Like gravity. Another way you can appreciate is the radiant field, a unidirectional field. Unidirectional field. right? Like a ray shooting out, radiant. Has no net circulation. Because when you take a closed loop, there are segments that are forced to orient in a negative direction. But your field is only one direction, unidirectional. So the work done on these two paths will be cancelled out, giving you no net circulation. Right? So the better way to understand this null identity is the curl operation on the gradient of a scalar field. The gradient is trying to find the maximum change. So it's perpendicular to your surface. Okay, so if you walk on this contour, there's no contribution. And because you perform the gradient, so the resulting vector field is unidirectional. Right? Second null identity. Divergence of a curl is always 0. How to understand it? Well, curl operates on a vector. So the apparent difference as compared to the first one is this one operates, you start with a scalar field. But this null identity is focusing on a vector field. Think about it. What is the physical meaning of divergence? Curl of A is a vector field, so you can apply divergence on it. So if you have a vector field and you try to evaluate its divergence, what does it mean? Divergence, again, is trying to measure the net outward flux within a small volume, right? Like the flow of water, the magic water faucet that I showed you. But what type of operation is curl trying to sense? If you have a vector field, you perform its curl operation and it is not 0, which means now you should be able to understand it and explain to me. If you have, so this curl of A is not equal to 0, right? Your curl of A is not equal to 0 means you have a circulating field, right? You have a circulating field, but now you're asking me to evaluate the divergence of this circulating field. Just imagine, I have a box. I have a magical box. I open the box, I have something circulating inside. Okay? So you ask yourself, oh, I have a circulating field inside the box, so how much of that field is flowing out of the box? 0. Right? By performing this curl operation, you're trying to find the components that gives you circulation in A, right? So after you perform this operation, you only have a circulating field, and now you want to have a box to surround it, and you want to have fields flowing out. It's impossible. So this second null identity means divergence. You're trying to sense fields flowing out, but unfortunately, you performed curl operation first. You try to find the components of A that's circulating, so it's not flowing out. Right? So these are the physical meanings behind these two null identities. So if you understand divergence operation, you understand curl operation, you understand gradient, these are actually very natural. again, divergence of a curl is equal to 0 means you have circulating field, right? Once you have circulating field, there's no divergence. So try to read this sentence. Divergence free means divergence of the vector field is 0, means divergence free. It is a circulating field. A circulating field in a more academic nomenclature is a solenoidal field. So a solenoidal vector field can be expressed as the curl of another vector field. This is 2D. Okay? This is for you to come back and read. So as we move into magnetic field, this will become important. But for now, I just want to tell you a vortex field or a circulating field is like a vortex, 漩涡. Okay? A circulating field, a vortex field, has no outward flux. Right? Circulating field, like a vortex, 漩涡, does not flow out. So the physical meaning is if you have a vortex field, its divergence is 0. If you have a radiating field, it is derived after performing gradient over a scalar function. There's no curl, there's no net circulation. Alright? Finally, you are launching into the official content. All the previous topics are more like a background information. Yeah? Question? Right. There is one last page on the previous chapter, which I skipped because it's not really giving you a lot of information. But you can keep it. You can just read it on your own. It's just saying a field can be comprised of two parts. One is conserved, one is non-conserved. Because eventually they are curl operation and divergence operation, they are commutative. So basically it's just saying that a field can have two components. Okay? So if you perform divergence, the conserved field, the conserved part will give you a non-zero divergence. On the other hand, if you perform the curl operation, the non-conservative part will give you a non-zero result. That's it. It's just a linear superposition. Okay? But thank you for your question. Does that answer the question? Yes? Okay. Alright, so now we're moving into the textbook, chapter number 3. It's entitled Static Electric Field. So I prepared 3 PowerPoint sets for this chapter. So the first PowerPoint set is discussing about electrostatic fields in free space. Free space means there's nothing. In the space considered, there's nothing. Vacuum. Right? So the structure of the textbook and for our following class is we are going to investigate into static electric fields. Okay, electrostatics means static electric fields. And then the next topic is static magnetic field. Right? Then in the very end, we are going to combine these two, electric field and magnetic field, to electromagnetic field and time varying. So when you have time variation, you really have a wave. Right? Think about the transmission line you learned. We have a wave. A wave depends on time and location. But it is easier for us to understand static, meaning there's no time variation. So in the end, we want to understand how a wave behaves, but before that, we need to have deep understanding to the statics. Now the way the textbook is trying to describe E field and magnetic field is, for each field, it teaches you electric field in free space. There's nothing. Okay? So my first part point set is electric statics in free space, and then electrostatics heavy materials. What are the effects? For example, you have electric field in water, in glass, in silicon. What are the differences? Third PowerPoint set will be focusing on boundary conditions and electric energies. Right? So 1, 2, and 3. So these divisions would also apply to magnetostatics as well. Right? So there will be 3 PowerPoint sets for electric fields and another 3 for magnetic fields. Okay. So today, according to time, I could probably cover up to fundamental postulates and maybe Coulomb's law, maybe. So there are 2 fundamental postulates. Only 2. And now you have to think, this is based on your maybe previous understanding to electric field, but I really want to relate our understanding to electric fields to the 2 null identities. It happens to be that the very reason we emphasize on the null identity is it's strongly related to the field distribution. And I can give you a hint. One of the null identity is directly related to electric field, and the other one is directly related to magnetic field. So before I reveal the secret, take a guess. Which one of the 2 null identities is related to electric field that we are talking about now?